Oh my gosh, entertainment.
Welcome. I'm just writing some stuff down right now. We're gonna get started about 5 after. So I would recommend having WebAssign open. We're gonna work on practice exam version 3. If you have specific questions at any time, shout them out. If you've already worked on something and want to go over it, shout it out or whatever. So that's probably a good idea. Okay, so you guys may not all have 5 versions of the practice exam. They all have very, very similar questions. So when I say we're gonna do number whatever, go to that number and it should be the same exact type of question, just with different numbers. If it's not, say something and we can try and figure out how to make it work the best we can. Okay? All right, let's go ahead and let's get started now that it's 5 after. So sorry for the confusion. We will be working on practice exam 3. I have 5 versions of it. Some of you guys have 1. It just kind of ranges based on professor, but these questions are all very similar. So when I say I'm going to be working on the practice exam, I'll tell you what number we're going to be working on, or number that I've chosen, and it should be very similar questions. At any time, if you have questions, feel free to put them in the chat. You guys in the room, like I said, shout them out. With that being said, this practice exam is going to be very, very helpful. This practice exam is going to be very, very similar to what you will see for the real exam. So it's a good way to study. I have between 4 and 5 questions picked out to go over from the practice exam. We'll kind of see what time dictates and what other questions we have. So yeah, without further ado, let's get started. So for exam 3, there are 5 sections that we really need to hit. There's 6 if you consider 11.1, which is going to be sequences. But series take precedence. Sequences kind of, if you know how to do series, sequences are just going to be essentially the same thing, a little bit easier. So I'm going to spend a lot more time on series. So we're going to start in Section 11.2, working with geometric series. So the biggest thing we need to know is how to find the sum of an infinite geometric series. The sum is going to be this formula right here. Our sum will equal A over 1 minus R, where R has to be, the absolute value of R has to be less than 1. If it's greater than 1, we are going to have a divergent series that will not have a sum. And A is equal to the first term of our series. So that will be the first section on the exam. Second section, we're going to be dealing with the ratio test. The biggest thing to remember with the ratio test, take the limit as n approaches infinity of a sub n plus 1 divided by a sub n. Now, I like to say, instead of dividing by a sub n, multiply by the reciprocal. So what we would have, if I just make something up real quick, x to the n, I'll make something up. We'll just say a n equals x to the n divided by n factorial. So if I plug it into this formula, we'll have x to the n plus 1 divided by n plus 1 factorial times now n factorial over x to the n. And that would be absolute value. That's going to be a lot easier to write this way. So essentially, you're just flipping your series summation and multiplying. It's going to be a lot easier than trying to divide, gets rid of a lot of fractions, makes stuff easier to cancel out. From there, you will be going to power series. So power series, we're going to be thinking about the geometric series quite a bit, or we're going to be thinking about our ratio test. And from this, we're going to be looking to find a radius of convergence. A lot of times use ratio tests, every once in a while you use geometric series. I would focus more on ratio tests. So in this case, we would take this limit as n approaches infinity, and we would get it in terms of x, and that always has to be less than 1. So then we would solve for x, and that would give us our radius of convergence. Okay, and then we get to the fun stuff of Taylor series and application of Taylor series, so Maclaurin series and stuff like that. So Taylor series, you're going to be giving questions like find a series centered at a equals this, and you're going to be given some function. My recommendation, make a table. Make a table, you're going to have an n, you're going to have f prime of n, and then you're going to have f prime of, f prime of a, f to the n should be derivative of a. So when we have n0, we'll just have f of n, and we'll so forth. So n is 1, we'd have f prime, n is 2, f double prime, so forth, plugged in at that a value. That's going to help us. We'll write that out, and that will help us to kind of see a general formula. And then finally, applications of Taylor series. This is the homework you guys have due tonight. And in this, we're going to be thinking about approximating some functions with a t sub n polynomial. And from that, we then are going to say, what is the estimated accuracy of this t sub n polynomial? Those are the 5, 6-ish sections on the test if you include sequences. But these are the 5 that really need to be touched on. So that being said, I'm going to go ahead and jump to a new sheet of paper. I will put this back up at the end if you guys want pictures of it or whatever else. Do you guys get a note card for the exam? Okay. Okay, you get that. There is a little sheet that you guys get with equations. So I will put this back up if you guys want to copy it at the end. Without further ado, let's go ahead and let's get to a practice exam. So the first question I had picked out was number 4 from the practice exam. And this is saying, find the values of x for which the series converges. Enter your answer using interval notation. So on my screen, I have summation n equals 1 to infinity of -3 to the n times x to the n. Okay. So here we need to think about, okay, what can we do here? And I said there's 2 different ways to think about it. We can think about using ratio test or geometric series. In this case, we can rewrite this as -3 times x to the n. And when we see something like this, I want you guys to think geometric series because we have something to a power. So now we need to think about, okay, what the heck do we have going on when we think about this? Well, -3x is going to be our radius because that's going to be consistent in every single term we have because we're taking that to the nth power. So r then equals -3x. And if we think about our first term, we want to start at n equals 0. So if we want n minus 1, we're going to have -3x times -3x to the n minus 1. So a then will equal this -3x. So -3x equals a. All right. So from here, now we need to think about where the series is going to converge. And if you remember from that first sheet, I said the absolute value of r has to be less than 1 for our series to converge. But we know r then is -3x. So we can say the absolute value of -3x has to be less than 1. If we want to get rid of these absolute values, what we're going to do is we will say -1 is less than -3x is less than 1. Okay, and simply from here, what we're going to do is we are going to divide by -3 on each side of this. So we'll divide by -3, divide by -3, divide by -3. When we divide by a negative, our greater than signs will change. So now we'll have, if I do this all out, I'm going to have equals 1/3 is greater than x is greater than -1/3. Okay, and they want us to use, for what values of x does a series converge using interval notation? So in interval notation, we would say that we will converge for -1/3, 1/3. So for in between those values of x, we will converge. Now, they want us to also find the sum of the series for those values x. So to find the sum of our series, we're simply going to use this sum equals a over 1 minus r. Okay, and we set up here what a and r are going to be. Sorry, I'm off the page. So we're simply just going to plug them in. So if we plug them in, we'll have equals a is -3x divided by 1 minus -3x. And just cleaning it up a little bit, that should be a -3x. We have -3x divided by 1 plus 3x. And that right there will be the sum that we will converge to. So that's a good little warm up with seeing our radius of convergence, doing some geometric series work. Good question to study, good thing to know how to do, whether you have an x or not. You most likely will see something without an x that just wants you to find if it converges, and if it does, what's its sum. And then you most likely will see something like this where it wants you to find the interval of convergence and the sum of the series for the value x. So that is the first one I wanted to go over, first one I picked out. The next one I picked out, we're going to progressively get harder as a heads up, is number 6. So number 6, we want to find the radius of convergence r of the series, and then we want to find the interval of convergence of the series. So this is a similar question to the one we just did. Now you're going to see it's going to involve a little bit more work. So we look at our summation. We have summation of 6 to the n times n squared times x to the n. Okay. And we have n equals 1 to infinity. And I'm off the screen. Sorry. Looking at this, there's no way we can get everything in terms of to the n power like we did above. So let's kind of think about maybe doing a ratio test. So what we will say is we'll say a sub n equals 6 to the n times n squared times x to the n. And then we're going to use that lovely formula. I'll write it out here. Limit as n approaches infinity, a sub n plus 1 divided by a sub n. Now you really get to see some math here because this one gets fun. So what we have then is we're going to have limit as n approaches infinity, absolute value of a sub n plus 1. So everywhere we have an n, we're going to add plus 1. So we'll have 6 to the n plus 1 times n plus 1 quantity squared times x to the n plus 1. Okay. And now how I said multiply by our inverse. In this case, since we don't have a top and a bottom, it makes more sense just to divide by HBN. If we had a fraction here, then we probably would multiply by the reciprocal, but because it's just a single term, it's easier to do it this way. I can show you how it'd be done the other way. 6 to the n, n squared, x to the n. So real quick little aside, if we wanted to do what I said before, multiplying by the reciprocal, you would have this here times 1 over 6n times n squared times x to the n, and then we would just combine the two since we're multiplying, and that's what you get. So now let's take a look at what we got going on here. So what's going to cancel? Well, right away, this 6 to the n plus 1 divided by 6 to the n, we have one more 6 on top than we do on the bottom. So what I'm going to do is I'm going to cross off these n's, and we just have 6 to the 1, so I'm going to cross off that 6 as well. So I'm going to do limit as n approaches infinity of 6 on the top. Then let's think about our next term here. We have n plus 1 squared over n. That's not going to cancel at all. There's nothing in that we can cancel. So we're going to have times n plus 1 squared divided by n squared. And then our bottom, our last terms, we have x to the n. So that will cancel with x to the n, and we'll just be left with times x. Okay. So now we need to think about our absolute value. Our absolute value now gets a little bit weird. So any of these terms here are numbers. That can't change. That's not going to change no matter what we plug in. What's going to change is our variable x. Oh, sorry. Thank you. Yell at me if I do that. Okay. So what's going to change is our variable x when we plug in numbers. So we're just going to put absolute values around x because that's the only thing that's going to be dependent at this point in time on what we have. So now if we think about taking our limit as n approaches infinity, what do we have? Well, that 6 isn't affected by n. This n plus 1 squared is, and this n squared is. Well, we have n to the same power in top and bottom. So we think about our coefficients in front of our n squareds. We have a 1 and a 1, so we just simply have 1 over 1. So that limit then equals 6 times absolute value of x. Okay, now from here, when will this series converge? So we know that that limit has to be less than 1, so we'll say that that has to be less than 1. I'm going to rewrite down here. We're going to have negative 1 is less than 6x is less than 1. Divide by 6. Negative 1/6, comma 1/6 is going to be our interval of convergence. How about our radius of convergence? So our radius of convergence is simply just backing up a step. We don't think about this absolute value. We just have 6x equals 1. So our radius of convergence then is 1/6. You can also think about it. You think about it here. Think about our middle term, which is 0 in our case. It's just half of that, half of our total interval. So now we have radius of convergence. And we have interval of convergence. Again, good question. Essentially, it's asking the same thing. You can see that that one's a little bit more difficult with a lot more work. That the ratio test can get a lot. It can turn into a lot real quick. So next, the next one I have is, we're not going very far. This is going to be a general Maclaurin series. So it says number 7, it wants us to find a Maclaurin series f of x, or find a Maclaurin series for f of x using the definition of a Maclaurin series. Assume that f has a power series expansion. So our function f of x equals 5 times quantity of 1 minus x to the negative 2. And essentially, it just wants us to then find f of x equals the summation from n equals 0 to infinity of what? Okay. And then it's going to also want us to find our radius of convergence. We'll work on that right after. So let's get started. As I said in the beginning, make a table. So we're going to have n fn of x, fn of 0 in our case. Let me make sure of that. We are on question number 7? Yep, okay. So find the Maclaurin series. So Taylor series, Maclaurin series is always centered at 0. So I'm going to write up here a equals 0, which means we're going to be plugging fn of 0. Maclaurin series is the Taylor series application, always centered at x equals 0. So that being said, let's go ahead and let's fill out this table. So n is 0, 1, 2, 3, 4, and so forth. This is a fun process. So the first one, we just simply have 5 times 1 minus x to the negative 2. And when we plug that in, we get 5. Think about our next one. We're going to have 10 times 1 minus x to the negative 3rd. Plug that in, we get 10. Next one, we're going to have 30, not negative 30. So we have a negative x in all those, times 1 minus x to the negative 4. We're going to get 30. Think about our next one, 120. 1 minus x to the negative 5th. We're going to get 120. And then the last one, another derivative. So I'll show you how I get this derivative. Derivative of 1 minus x to the negative 5th is negative 5 times 120, which is negative 600, times our derivative of the inside. This function here, 1 minus x, derivative of minus x is negative 1. So that's how we get 600 times 1 minus x to the negative 6th. That's 600. I kind of went through that quick, so let me just go through the first derivative real quick. 5, 1 minus x to the negative 2. Okay. What I like to think about this is the outside function and inside function. So first I need to take a derivative of my outside function. My outside function is this whole thing. Derivative of this whole thing is negative 2 times 5 times 1 minus x to the negative 3 times derivative of my inside function. My inside function is simply this 1 minus x. Derivative of that is times negative 1. And that's how I get 10 times 1 minus x to the negative 3. Hopefully I didn't go through it too quickly, but that's kind of a little bit more explanation. So now from here, what we're going to do is we're going to start to think about what we have going on. So when we start to write out this series expansion, we start out with f of 0, then we have f prime of 0 times x plus f double prime of 0 divided by 2 factorial times x squared, and so forth. So if we go ahead and write out these terms now, f f of 0 is 5, so we'll have 5 plus 10x plus 30 over 2 x squared plus, we have 120 over 6 x cubed plus 600 divided by 24 x to the fourth plus, and we continue out. Let's go ahead and simplify this down really quick so we can kind of see what's going on. 5 plus 10x plus 15x squared plus 20x cubed plus 25x to the fourth and so forth. Okay, right away we can factor out a 5. There's a 5 in every single term, which means that there is going to be a 5 in every single term. So when we go ahead to write out the summation, we're going to have equals summation. I'm going to toss a 5 out in front. We're factoring out 5. And now if we think about what's going on next, factor out a 5, this is going to turn into 1 plus 2x plus 3x squared plus 4x cubed. So we're just increasing by 1 with every single term we do. So we're going to have n equals 0 to infinity. Thinking about this first one is 1. This first term is 1. We're going to plug in n equals 0. So we're going to want to have an n plus 1. Let's think about that again. When we have n plus 1, when n equals 1, we're going to get 2. Perfect. N equals 2, we get 3. Perfect. Okay, now we need to think about that x. How do we get that x to make sense? We're going to multiply by some x here. And now we need to think about some power that we're going to have. So this first one, there's no x. And n equals 0 gives us no x because anything to 0 is 1. So let's think about x to the n. X to the 0 is 1. X to the 1 is just x. X to the 2 is x squared. So this then would be our general formula for this Taylor series or Maclaurin series. Now, from here, what we would need to do is we want to find our radius of convergence, which means we will perform another ratio test. So let's do that really quickly. Not really quickly, but semi-quickly. We'll have limit as n approaches infinity of a sub n plus 1 over a sub n equals limit as n approaches infinity of 5 times n plus 2, because we have this n plus 1 gives us n plus 2 times x to the n plus 1 divided by 5 times n plus 1 x to the n. All right. So now we think about this limit as n approaches infinity. Well, let's think about cancels first. We're going to be left with a single x up top. 5s will cancel. Nothing else cancels. Let's rewrite this one more time. Limit as n approaches infinity. N's are numbers, so they don't need to be in the square root. We have n plus 2 over n plus 1. X is some sort of function, so we want that in the square root. Limit as n approaches infinity of n plus 2 over n plus 1. We have the same power. Look at our coefficients. They're both 1. Going to cancel, so we're left with absolute value of x. Now to find our radius of convergence, we're going to say absolute value of x for values to converge has to be less than 1, meaning that x equals 1. That is an R. X. Thank you.
Also, do you need absolute value, not square root?
Yes, sorry.
Thanks for the catch, Blaine.
Yes, good catch. Sorry, I'm talking fast. So we know that our radius of convergence is equal to x equals 1. So again, this radius of convergence stuff, this ratio test doesn't go away. You're going to see it over and over and over again. So I definitely would recommend getting well caught up on that and really understanding how to do your ratio test. So the next question I have for us is going to be number 9 on the homework or on the practice exam. Number 9 is a fun one. Sorry, we're on the green paper now. Number 9. This is similar to homework you would have seen that was due the 13th last Friday, using a series to evaluate a limit. It's a fun one. So I was given limit as x approaches 0 of a nasty looking thing, 1/3 x cubed minus 1/2 x squared plus x plus, minus, excuse me, minus natural log of 1 plus x, all divided by x to the 4th. Okay, so we want to evaluate this limit. The only thing here that has some sort of a series is going to be this minus natural log of 1 plus x. Now, if we go into the book and on an exam, you would provided a table with these. If you have some series like this, you will be provided with it. Don't quote me on that quite yet. Let me make sure of that real quick. Maybe not. You may need to know this. You may need to know these formulas, so I would take a look at these formulas. I will pull them up at the end in the book, so it's going to be the easiest way for me to display them, and I will put them on the screen. So you're going to need to know these formulas for Maclaurin series. There's a handful of them to know. Yeah. So we're not going to mess with this 1/3 x cubed or anything else that we have going on. We're simply going to be messing with that minus natural log of 1 plus x. So let's rewrite this now, and I'm just going to expand this natural log of 1 plus x series, and then we can go from there. Limit x approaches 0, that's infinity. Sorry. X cubed over 3 minus x squared over 2 plus x minus, I'm going to do big brackets like this, so we know that's what we're expanding, x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus x to the 5th over 5. I don't think I need to continue on. I think you guys can see what's happening there. All divided by x to the 4th. And now something interesting happens here. We have this negative sign that's got to get distributed to everything. And if we look at what we have in front of this, we're going to have plus x minus x. Those will be gone. This minus turns this negative x squared over 2 into a positive. We have a minus. Those will be gone. Same exact thing with our x cubes. So we're just left with, let's distribute this to that guy and to the next guy and so forth. Rewrite it, limit as x approaches 0 of, no, it's 0. It is 0. Yep, it's 0.
Hey, Kelton, before you get too far, real quick question.
Or is that just that negative sign distributed?
That negative sign distributes to every single part of this. So those are going to cancel. We will have different signs. It is 1/4 x to the 4th. Yes, this is correct so far. Everything is correct so far. We're going to distribute this negative sign to everything. So let me get to the next step, and then I'll see if that clears up some questions that have come up.
Hey, Kelton, how do you know how to get that series out of the from the ln 1 plus x?
Come again, I'm sorry, 1 second, Keaton, you're a little bit, the
Muffled.
audio is a little bit low in here.
Okay.
Go ahead and ask again.
When you went from negative ln 1 plus x, how did you know to go to the x squared over 2 to that series?
So there's a table in chapter 11, I want to say it's section 10 or section 11 that has this specific expansion, and there's a handful of other ones. So that table, I can find it real quick for you if you want, and I'll show it to you guys.
Table 1.
Yes, it's table 1 in section 11. Table 1 in section 11:10. I actually opened up right to it almost. That's what you're looking at. So this natural log of 1 plus x, that's where we get what we have there.
Okay, I see what I was missing now. Thank you.
So take a picture of this because it's helpful. You may need it. The only thing you don't need is this last one here. You don't need the binomial series. Yes. Okay. So anyways, that's where that all comes from. Now let's clean up some of this confusion with the negative sign. This negative sign gets distributed to every single term in this series expansion. So this negative turns this into a negative x, turns this into plus x squared over 2, turns the next thing into a negative x cubed over 3. It will turn this next term into a positive x to the 4th over 4 and a negative x to the 5th over 5. So if I rewrite this now with stuff canceled, we'll be left with plus x to the 4th over 4 minus x to the 5th over 5 plus so forth. And then we're divided by x to the 4th. Okay. So now simply what we can do is, not simply necessarily, what we can do next is we can think about, okay, what do we have in all of these terms that we're seeing? We're seeing that we always have an x to the 4th or higher end, so we can pull out an x to the 4th from the top and the bottom. If we do that, I'm not going to write the limit real quick. I'm just going to write this as x to the 4th times divided by x to the 4th. If we pull out an x to the 4th from the bottom, we just have a 1. And then if we pull out an x to the 4th, we have 1/4 minus x over 5. I'll do one more term, plus x squared over 6 minus, and it would continue on. So you see that factoring out the x to the 4th leaves us with 1/4, leaves us with an x next, and so forth. So now I'm going to write limit, and then these will cancel because you have x to the 4th over 4, or x to the 4th over x to the 4th, they will cancel. So limit as x approaches 0 now of, and this 1 on the bottom just means we have the top, 1/4 minus x over 5 plus x squared over 6 minus so forth.
Give me the
Now,
paper, please.
come again?
Can you mute the paper up, please?
Oh, yes, sorry, thank you. Okay, now if we plug in a 0 for x, it's not going to affect this first term, but you see every other term we have has an x in it. So every other term we have is going to go to 0. So this limit then will equal 1/4. That is how you go about a question using series to evaluate a limit. It's a lot of work. Yeah, it's a lot of work. But there's tricks like this up here where everything cancels here, and then we're just left with an x to the 4th term and so forth. And then we pull out an x to the 4th from the top and the bottom to get, so we have just actual numbers. All those are tricks that you're going to want to keep in mind, keep an eye out for on the actual exam, because most likely you'll see stuff, maybe not similar, but you're going to see something where you're going to have to do tricks like this to get to something you can evaluate to give you a numerical answer. Okay, so I have one more question that I pulled out. I guess first I should ask, are there any questions, any specific questions anyone wants to go over before I do this last question? Because this last question is going to take up a remainder of the time.
What was that question? What was the wording on that question?
Okay, the wording on that question. So it asked, use series to evaluate the limit. Yes. Go ahead, ma'am. Sorry.
For the radius of convergence,
Yeah.
the interval of convergence, is there a radius of convergence, just the upper boundary? That's what it usually seems to be.
Yes and no.
Okay.
When you're multiplying, so let's go back to one of those. Let's go back to this one right here. So the question was, is our radius of convergence always just like our upper limit, our upper bound for interval of convergence? The answer is no, but the answer is yes for what you see.
Okay.
For what you guys are going to see, it's almost always yes, but that's not the case. So, for example, if this, instead of being 6 times the absolute value of x, was like 6 times x plus 3 absolute value, we would have a different interval of convergence, but our radius would still be 1/6.
Oh,
So essentially, if we did solve this out, we would see that we'd have -2 is less than 6x less than, oh, it should be -4, sorry. -4 is less than 6x is less than negative, oh my goodness. I promise I'll get it. -4 is less than 6x is less than -2. When we divide by 6, then we're left with -2/3 is less than x is less than -1/3. And like I said, the radius is half of your total interval, which our total interval for this is 1/3, which means our radius is 1/3 divided by 2 is 1/6.
So your radius, the magnitude of your radius is going to be half of your interval.
Yep.
But your interval doesn't necessarily always start at 0,
Right,
or it isn't centered around 0.
that's a
So
good way to put
your
it.
radius won't always just like automatically.
Right. Right, so this, essentially what this +3 does is it changes where you're centered at. Yeah, so when you add or subtract from x, you're gonna change what you're centered at. That's a good way to put it, I like that one. Okay, did that make sense to everyone in chat as well, or everyone in Zoom land as well? Good question, very good question. Okay, perfect. So then let's do, I'm trying to decide what one I want to do, 10 or 11. Let's do 10. We may not make it all the way through 10. If you guys got to take off, feel free to take off. You're not going to hurt my feelings at all. But we're going to try and push this as close to 8 as we can. And then I will put back up the little intro that I'll put back up the table actually at the end. So without further ado, number 10. Find a Taylor polynomial T3. So we want to find a T3 of x for the function f centered at a. So our function f of x equals x times e to the -5x centered at a equals 0. That was nice. Okay. So Taylor polynomials, make a table. Easiest way to do it. N fn of x and fn of our value a, which happens to be 0. So we have 0, 1, 2, 3. And we only need to go to 3 since we want a T3 polynomial. We need to go to our third derivative. So our first one is x e to the -5x, which is going to be 0. Next one is 1 minus 5x times e to the -5x. And that value is going to be 1. I didn't leave myself a lot of room. I apologize. Next one is 25x minus 10 times e to the -5x. It's going to be -10. And our last one is 75 minus 125x e to the -5x. These derivatives are all product rules, just so you know. So then we'll have 75. So now we want to write out our T3 series. So what we're going to do, is we're gonna have our first term is 0 plus our second term 1 times x to the first. And it's really 1 over 1 factorial times x to the first, plus our second term, negative 10 over 2 factorial times x squared, plus 75 over 3 factorial, x to the third. Okay, so if we simplify that, we would be left with x minus 5x squared plus, x minus 5x squared minus 25 over 2 x cubed. And that, sorry, thank you. I'm terrible at that. I apologize, guys. That simply is going to be our Taylor polynomial t sub 3x for the function. Now, they want us to graph this. You don't have, better hold my teeth when I say you won't have to graph it, because you most likely will. So let's think about what we got going on here. They want us to graph this. Let's take a look. Well, that's interesting. Let's take a look at what we got going on here. So let's think about our cubic graph. Our cubic graph is going to look something. This is just a general cubic graph. It's going to look something like that. Let's see what we have going on here. So that's the weird part.
It's not flip.
It should.
Yeah.
But I have two different answers. Okay. This should be plus. This should not be minus. I'm not sure where that, my head is in a different world right now. Obviously that's plus because we have 75 over 3 factorial times x cubed. That's going to be positive. So that's not going to change anything. So we go ahead and we think about, okay, what's going on? What do we have going on with this graph then? Next, what I would do is, okay, so I'm looking at this. We've eliminated 2 answers so far. We have only 2 graphs that look something similar to this. So now we need to think about our last one. And if I look, it's hard to explain a graph in question on WebAssign, but essentially, if I look, one of them goes like this and comes back up, and the other one just simply goes like this. So from here, what I would do is, okay, we want to find our x-intercepts. We want to find when x is 0. If we have x is 0 at one point, we're going to choose this one. If we have x is 0 at 2 real points, we're going to choose this one. So what I would do then is I would take this function above. I'm going to write it below. X minus 5x squared plus 25 over 2x cubed. Set it equal to 0. There we go. Factor out an x. We'll have x times 1 minus 5x plus 25 over 2x squared equals 0. If you do this, you'll find that there are no real roots that come out of this equation here. So the only real root is x equals 0, which means we're only going to cross our x-intercept in one place, and that will be at x equals 0. So that's kind of the way to approach that. It's a little bit far-fetched, but you're probably going to see something similar on an exam. So just so you guys know. Yeah, so that's how you go ahead and do that question. That being said, that is all the content I have for y'all today. I am going to put up this table that I said I would at the beginning. If there's no other questions, you guys are free to go. If there's questions, I'm here, ask away, please, and I can kind of clarify, hopefully. If not, that's a good table to have, because most likely you're going to have a value to limit using series. No, they have different material covered or planned. It's going to be similar because I would imagine they're going to be pulling from this practice exam, but they will perhaps most likely have different material and different ways of explaining stuff. So it may be beneficial if you have the time to stick around. Because if I said something that doesn't stick, if they have a different way, maybe that will help. So, but it is going to be a different, I am going to close this Zoom meeting, and there will be a different one. Okay, you want me to go over that table?
That's the table.
So essentially, all this table is saying is it's saying, if we're given this function, this is going to be our Maclaurin series expansion of this function. So this should be the same table that's in the e-text. I don't have access to e-text, but this should be the same table.
Is that table correct?
What's up?
Does that table?
Yeah, is this table correct?
Yeah,
Okay,
we've seen that table.
Yeah.
cool.
Yes, you have seen the table. Yeah, I guess Keaton, if you're confused with it still, I'm a little confused with what you're asking because I would imagine this is the same table that's in the e-text. I can take a look real quick.
It should be in our like worksheets that we go through.
Okay.
It might be set up because they record the text of this last week.
Yeah, okay.
It might just look a little bit different.
Right. So Keaton, I guess, is it similar? Does it look similar to what you have for that table? I'm looking right now and see if I can't find it. Okay, you got it. Perfect. All right, awesome. You are all free to go. I will be closing the meeting real soon. The next one will be starting in 5-10 minutes. Thank you guys for coming. Good luck, everyone. Good luck on the exam. And yeah, that's all I got for you guys. So thank you all for coming.